Yep, it's on the board. Just there, yeah, that's what we studied. We were looking at the law of conservation of energy. So everybody happy what they have to do for that prior research question? Just answer those questions that are there. All right? Move on. Your calculations. Now, I used this kid's crack, but we didn't use a ping pong ball. Okay? Mainly because I couldn't find a ping pong ball. I could only find the balls that we had. So, from the table, he told me that the mass of the ping pong ball was 2 grams. Now, that's a real problem because when I'm using this formula, the mass needs to actually be in kilograms, not grams. So, we go, some of you need this information, from grams to kilograms, we divide our number by 1,000. So I'm going to divide this by 1,000, which is going to give me 0.002 kilograms. Happy? Okay, so all your masses will need to go through that conversion. And the way to change it from grams to kilograms is to divide the number by how much?
1,000.
1,000. Brilliant. Okay. So EP was equal to the mass, well, 0.002 times G. Does anyone remember what G is?
9.8.
Yep, it's the acceleration due to gravity. Will it ever be any different than that number?
No.
So technically, could I write this formula like this? Yeah, I've got no problems if we want to use it that way. So G is 9.8, and then we had a problem with the height too, because height had to be in meters, and I know that this kid's ramp was 75 centimeters. Now there's a problem because that's not in meters. So how do I go from centimeters to meters?
Divide by 100.
I divide this by 100. So every one of your heights you're going to have to divide by 100, and every one of your masses you're going to have to divide by 1,000. So this is going to become 0.75 times 0.75. So can someone put that in the calculator for me, please? .0147. Yep, that's right. And the units, of course, are joules. So, according to this practical, I should get that for this, shouldn't I? Yep, okay, well, let's find out. So to find my EK, well, I already know my mass is 0.002. I just need to find the speed. How do we work out speed?
Distance divided by time.
Distance divided by time. Now, we knew the distance was 2 meters, agreed? So it is always going to be what on top of this calculation? Always a 2. Yep, that's always going to be the same. We're just going to need to put the time in. Now, the kid's time was 2.3 seconds. So what's 2 divided by 2.3?
0.87.
0.87 meters per second. And we needed to know this speed because it's in our kinetic energy formula. So then we're going to times this by 0.87 and we're going to square it. Who can tell me what that is, please, in the calculator? $7.569. Another 0.7569.
Probably is.
That's why I require more than one person to do it. .000. Wow. Aren't they the same? Well done, kids. You've just broken the law of conservation of energy. That's it, I'm going home. The universe is going to crumble. Everything's going to fall apart. No, not really. Why is this a ridiculous result? They're not the same, they're nowhere near it, but should they ever be?
No.
What happens when you roll that ball down around? Did you hear anything?
Yes.
Yeah.
So that means that this energy is not being transferred into kinetic energy, it's being transferred into sound. Yeah. Did the ball push the air out of the way? Yeah. Is that going to slow it down?
Yeah.
It certainly is. So let's not talk too much about that, and let's go straight on to our discussion. So for your calculations, they're going to be exactly the same. You're only going to be changing a couple of values. You're going to change the height because, I don't know, if your ramp is 75 centimetres. You're going to change the mass because you need to change the masses of the 5 different balls that you did, but it's still going to be the same calculation. So all you got to do is just replace some values. You're only ever going to be changing this bottom number for the different times for the different balls that you've got. So this calculation is going to be the same as is this one. Okay, so you are doing a fair few calculations, but they're going to be exactly the same each time. So that, once you've done all those calculations, sum it up into a results what?
Table.
Table. Now, some people need help with the things. Can you know what you're doing? Can you give them help today, please? Because I can't get around to everybody. So if you know how to do these calculations for someone in here is struggling with it, can you just move next to them and show them what to do? All right? That's about helping each other learn. So let's go to the discussion. Oh my God. In paragraphs, write the following, in capitals, write no headings. I do not, in your discussion, want to see the word discussion and then science paragraph. No, 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 no. We don't need headings in a paragraph setting. Okay? Do we use dot points?
No.
No. Do we use full sentences?
Yes.
Can we put diagrams in?
Yes.
Yeah. Okay? Now, Miss Moore was super harsh on her kids. So if they did not have the 3 paragraphs, well, this one would be 4, but they didn't have the structure that she wanted, she gave it back to them. And I'm going to do it this time around. So if you get your prac back, it's got a big red thing that says resubmit. Something of this you haven't done correctly. And so I'm going to give it back to you. I'll tell you what to do, but then you'll have to resubmit it. So it's probably much better to do it correctly though.
That's fine.
Yeah. So the first paragraph is always going to be about the science of this experiment. So we tried to prove what law?
Law of conservation.
Which states that energy cannot be what?
Created or destroyed.
It can only be?
Transferred.
So that meant that we thought that our EP, our gravitational potential energy, was going to be the same as our
EK.
kinetic energy. Now, scientifically, is this right? No. Because what we didn't think about before we did this experiment, but once we've done it at the end, we can clearly see it's very much affected our results, is that we didn't think about air resistance, did we? None of you came to me and said, look, Mr. Robinson, when I roll this ball down the ramp, the ball pushing the air out of the way is going to create an error. Okay, because we just didn't think about it. Did we think about the friction of the ramp? And did we think about sound being a loss of energy? So if I drew this in an energy chain, geez, that'd be a good idea to put an energy chain in your experiment. I'd have gravpot, which stands for what?
Gravitational potential.
Yep, going to kinetic energy, because that's what I wanted, wasn't it? I wanted to change that gravitational potential energy into kinetic energy. But I've got a wide variety of energy loss. And remember energy change when we did them in our booklet, energy loss comes off the chain. Down, or you could have written it up, I wouldn't have worried. So where we lost energy was the air resistance. Okay, if you do that, you're actually losing energy because you're trying to push all the air that's sitting there in the way. The way I explain it to my kids is, let's say that there was one Big Mac in the canteen, and in front of you was every grade 7 in this school. You would quite happily push your way through all those grade 7s and get that Big Mac because you're grade 10 and they're grade 7 and you deserve it. So if you think about it, as the ball goes down the ramp, it's got to push all this stuff out. And as it pushes that stuff out, it loses energy. Friction is another way, and sound, of course, is another way that we identified energy being lost. So that's the science that you have to explain to me in a paragraph. Some kids said, could you give me a sentence starter? So I did. So I'll just talk about this one. The law of conservation of energy states that in this experiment, my gravitational potential energy should have been the same as my kinetic energy. This is a problem because the law of conservation of energy states energy cannot be created or destroyed, it can only be transferred or transformed. In this experiment, we didn't consider these transfers or transforms. So my potential energy as it rolls down the ramp is being transformed as it is hitting air resistance, friction and sound. There we go. That's explained it, hasn't it? Yeah. Now, let's see what this kid wrote. So, go to the first paragraph in their discussion, get a pen because you've got to underline some things and you're going to see where this kid went wrong. Thanks, man. It said each object started with a large number of gravitational potential energy than the results for the kinetic energy. Is that science or is that results?
Results.
So that is in the wrong what?
Place.
Paragraph. So just underline that first line because that's in the wrong place. That I would write in my
Results.
What's the problem with that though? Is it specific, the way they wrote that sentence?
No.
They've just said each object starts with a large number of gravitational potential energy than the results from the kinetic energy. Number one is they probably need to look at that sentence structure. Number two is it's in the wrong place. As seen above, the objects lose a significant amount of kinetic energy. Is that results or science?
Result. Science.
It's results, yeah. Okay, it's in the wrong section. Now, the other thing about this is that that kid has mentioned those things, but would it have been a much better practical report if they had simply put in the numbers? Like the actual numbers for these particular things. Here we go. According to the conservation of energy, energy cannot be created or destroyed, only transformed or transferred. Is that science or results?
Science.
That's definitely science. And that kid got heaps of marks for that because he actually sat there and named up the law and what it states. Don't forget to do that yourself. If we have a look here, it then said, therefore, in theory, the gravitational potential energy and kinetic energy should have been the same. Who thinks that's science? Who thinks that's a result?
Science.
It's definitely science. So the problem with this kid's practical is while they've given me what I wanted, they haven't been very specific about it, nor have they put it in the right section. Okay? If we have a look at their next paragraph, the results of this experiment are not reliable as the variables may have been measured incorrectly. Is that in the right place?
Yeah.
Inaccurate, yeah, sorry. Yeah. It is in the right place. It's in the results section, in that second paragraph where it needs to be. Is it true?
Yeah.
Then, yeah, that would be a lovely sentence. So if you're considering a sentence, you could probably use something along those lines. For example, the distance needed to calculate the formulas may have included the ramp, but some didn't. What's wrong with that?
That's an error.
That's an error, yeah. And so this kid's kind of writing the right things, but he's just put them all over the place. That's an error that should sit in the third paragraph. Furthermore, a 1 metre ruler was used, which may have not been as accurate as another form of measurement. That's definitely an error. But what I like the way is that they've actually listed up why they think it's an error. And so if you look at the whole thing, every part of that second paragraph, the kid's talking about errors, not about their results, which is a problem because like while they've produced an excellent errors paragraph, they've then gone in to do it again. These errors can be reduced in another experiment. Thanks, mate. Good. But hasn't put how. He said they could. You can do another experiment, get rid of these errors. Okay, excellent. How? What errors? So, the distances can't be measured specifically. The distances can be measured specifically by the millimetre, and the same distance can be calculated for everyone testing. A machine such as a light gate can be used to time accurately, eliminating the human reaction time. Why do I like that sentence?
Because it's
Excellent. Not only have they identified it as an error, and this is where a lot of kids go wrong, they'll say, oh, timing was an error in this experiment. Full stop. Now that tells me, yes, that's just listing an error. I can't give you any more than that because you just listed that particular thing. Tell me why it's an error. Okay, so we're going to have a look up here at our second section. Keegan, can you bring your laptop, please? Point to the ground. Everybody don't look at Keegan. You put it on there, and you two sit on the other side of the table. Hang on, I'll block it with my face. Okay, right, yep, good. All right. So, of your paragraphs, that is going to be the second biggest. This results section is going to be the smallest. Because it's just specifically telling me what we found out. So, if we look at this, the gravitational potential energy of the ping pong ball was 0.0147 joules. Have I named it? Where did this kid go wrong? What did he say? It was just large, didn't he? Large, not probably the greatest descriptive thing. However, its EK was 0.0075 joules. So I have specifically named up what I found. So the gravitational potential and the kinetic energy were not there. Now, if I was going to push it a little bit further, you're right? Okay. And I was going to go mathematical, I would probably say by a significant factor of 2 decimal places. Okay, because this is really, really much smaller than that. Like a Big Mac, if you ate it, is over 3,400 kilojoules. So the energy for this is 0.0147 joules. It's not a lot of energy. It would be very difficult, I think, even to measure that particular thing. So I did the ping pong ball, but then again, was that the only ball I did? No. So then I'd have another sentence that would specifically name up my results and what I'd actually found. All right? So, pretty simple paragraph, the results. Probably the easiest one that we're going to get. This redesign is where a lot of this work is going to be, and it's going to be 2 paragraphs this time instead of 1. Now, the reason it's going to be 2 paragraphs is because you can't write this one yet, because this is talking about how you're going to repeat this experiment on Friday. Remember, you're doing this again, and tomorrow I'm going to want that equipment list for what you want, so that you can repeat this experiment. Now, errors. Wow. Okay. I designed this experiment to be completely wrong for a very good reason. Because scientists generally don't come up with the right experiment the first time, do they? And there are so many things wrong with this experiment. Now, here are 12 errors that I've listed, but I consider that there are some more. Now, I'm not going to specifically name up them because I'm looking to give someone who's pushing for that well above to see if they can name up an individual error or one that I've missed. Are you all right with that? Okay, number 1. This practical is wrong. Fundamentally wrong from the start. If we remember from our booklet and our teaching, we have the max EP at the highest point, don't we? But where is the max kinetic energy? At the bottom of the ramp. Where did we measure it? Here. So is the ball losing or gaining energy as it goes along this 2 meters? It's actually losing it. So we haven't calculated the max EK. We haven't done it at all. And that's why our results are so wrong, because basically the experiment does not test what we want it to test. And this is what the challenge for you on Friday is to think how you're going to actually get rid of as many of these particular errors as you can. All right? So if we think about it, if I said stop, okay, now it took a little while for you to react. Okay, sorry mate, I know what it's like. Mr. Wilson does that to me all the time. But it took a while for my voice to travel from here to you. Now it travels pretty quick, speed of sound. It takes a little while to get into your ear, to then go to your brain, to then get you to react. Yeah. So if you're standing there and Bo's got the ball and he says to me, go, I've got to go, okay, he said go, okay, I've got to move my thumb and I've got to press the stopwatch. Now generally speaking, that's about 1.2 seconds. Big worry, especially one of the reasons why they don't like people playing on their phones when they're driving, because your reaction time is a big factor. If you're trying to juggle your phone and press the brake at the same time, your brain is not going to do it as quickly as if you just got to press the brake. So, reaction time is a problem because that means that our timing's wrong. And what calculation does that affect? Does it calculate our EP or our EK? Which one are we using time in? If you have a look at the board, which one did I specifically use time in? EK. So it means that these calculations are all incorrect in some way. Can we get rid of this?
Yeah.
In some ways we may have to just live with it. Okay, some of these errors we're just going to have to live with. Oh, I mean, person X. So when you walk past the video, don't let them see your face. Person X, who goes to St Brendan Shaw. Okay, fine, I'll try. Why is the carpet a problem? Friction, but also it's a massive problem in this experiment because you rolled down one medium and then you rolled it across another. Is that a consistent variable? No. So will the ball travel quicker down the ramp or across the carpet, you reckon? I reckon definitely the ramp because the carpet is actually going to do what? It's going to slow it down. You have the fibres on it. It's a British pit. Get out. Go back to your school. And so this is a problem for us because we changed their material and so we're not getting a constant speed across the two of them. If we look at number 4, bounce off the bottom of the ramp. So when you roll that ball down, there's a lip on that ramp, isn't it? And so that will hit into the carpet and that will make it lose energy. For the bowling ball, like the lawn bowls ball, come on, borrow that actually, please. That's actually going to help me. For the lawn bowl, it's not a problem. But your golf ball was like this one, a bouncy ball. So is it a bigger problem for some balls than others? Yeah, it's a big problem for that bouncy ball because, of course, it's actually turning that energy into what type of energy? Elastic potential. Good. I love the way you named it up. Nice idea to do it in your particular report as well. So balls, I've written balls, not full balls. I don't know why, but that's okay. I can't do everything. Now, is averaging and rounding an error? How many times have we average and round this particular thing? Yeah, we do it a lot because we're doing a lot of different calculations. Can we get rid of it? Yeah. It's going to be pretty hard because like you actually average things to try and make things a little bit more consistent. But when you average a thing, you actually get away from your experimental data, which could make an error. Is it a massive one? I don't think so. So I could live with that. A ball problem. Well, we did. What's the problem with the lawn bowl? Yeah, it's actually made to roll in a line. So if I roll the lawn bowl and I want to go 2 metres and the lawn bowl actually veers off in that direction, has it travelled 2 metres? It's gone further than 2 metres. And why is that a problem? Well, that's because in our EK, what did we say? That the distance was 2 metres. So we've got the distance wrong, which means our speeds are also wrong. So our speeds are a problem because not only have we got a problem with the reaction time, we've also got a problem with the fact that, where am I? Here. Yes, we've also got a problem with the ball not travelling 2 metres. Okay, sorry, brain just stopped there. The dodgeball, what do we notice about the big red dodgeball we tried to roll down the ramp?
It wouldn't fit.
It wouldn't fit. It didn't actually fit on the ramp. So it actually rolled down the sides of the ramp. Is that a problem? Yeah, because what's that going to do to the ball? It's going to slow it down. Yeah, so this could be a problem. Is it a massive problem? You know, well, that's what we're going to find out, aren't we, I suppose? Measurement. Did the ball travel 2 metres? No. It actually travelled X plus 2 metres. Didn't it? It travelled down that ramp. How long do you reckon that ramp was? It's taller than me, isn't it? If I stood it up, it's actually significantly taller than me. It's about 2.5 metres. So we actually should have probably done 2.5 plus 2. But that's still going to be inaccurate, isn't it? Because do we need this 2 metres? No. So my first redesign, if I was going to do it, is just to get rid of it. By getting rid of it, I get rid of a lot of these errors. Measurement. Wow. I broke a couple of kids' hearts today because I didn't do it for you guys, but in my class, whenever they weren't looking, I just went like this. I got the pen and I just moved it a little bit and then I just walked off. Then another kid had a piece of wood there and I just kicked it. I literally almost half a metre and the kid just walked to it and said, okay, yeah, this is 2 metres. Pretty mean of me. But the other thing I saw was kids do this. They got the metre ruler, they slapped it down on the ground, they said, yeah, that's about it. And then they kicked it across, got to here and said, yeah, that's about 2 metres. Did we measure this accurately? No. The other thing is, how did you measure the height? Because I saw a lot of kids measuring from the bottom of the table to there. Is that the height of your ramp?
No.
No, you've actually missed out probably at least a centimetre. It's a centimetre high. That's going to affect our things, not greatly, but you need to be super careful when you redesign this about how you measure it. The more accurate, the better. Yeah. Our speed calculations are all wrong. Why? What's the distance I put on the top there? 2 metres. Did it travel 2 metres? No. Many of you looked at me funny when I said that you had to time it from the top of the ramp to the bottom of here. Many of you looked at me funny and I was a little bit worried that I was going to have to tell some people, shh, wrong. But you didn't time the ball travelling 2 metres. It's travelled significantly further than that. And what actually compounds that is the path of the ball. You're going to say it's going to travel 2 metres, did it travel straight down the line that you measured? Now, most of the time the ball went like this. It went down the ramp, went bang, 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 and then shot out that way. And we went, okay, that's 2 metres. Is it? No. Okay. So the path of the ball is pretty difficult. And then, of course, the force used to release the ball. Some people can't help but just go, wonder how quickly this ball can go through a window. And they throw the thing down, or they don't just drop it. Now is dropping a problem too? Yeah, because you've increased the height, and also it's going to bounce. So it's very difficult to think about how you're going to release that ball so that it's not going to have some force actually put on it. And air resistance, is this the problem? Yeah. It's destroyed our results. Okay? It's one of the biggest problems in this experiment, I reckon. 13, work them out yourself. So, if I was to do the following thing, get rid of this 2 metres, what errors have I got rid of, and which ones do I still have? So let's go through them. Have I got rid of the practical being wrong? Sure, I get rid of that 2 metres? Okay, so, but the design is getting a lot better, isn't it? I'm not worrying about this wastage here. Can I change my reaction time? No, I'm going to have to live with it in this particular experiment. Can I change, have I got rid of carpet? Yeah, because I'm not using it anymore. Have I got rid of the bounce from the bottom of the ramp? Yep. So that's 2 errors I've got rid of. Good. I'm going to tick the ones I can't get rid of and cross the ones I can. Can I get rid of average and rounding? Probably not. I'm just going to have to live with it. Can I get rid of the ball problem? No. Well, I can. Because I just don't use the lawn ball. Or I just don't use that. Or I bring in another ball for myself. Okay, it's like a tennis ball would work quite well, although the fluff on it may be a problem for your experiment. But probably of all the balls that we use, which one do you think is the best?
Marble.
The marble, yeah. It's small, less air resistance, it's hard, it doesn't have that bouncy elastic problem that we have with the other ball. So we could select the ball that would make it easier for you. What about the sides of the ramp? Well, I've still got it, so I can't get rid of it. So I'm going to have to, what am I doing? Picking the ones I've got to keep. Yes. I can definitely measure better, and I don't have to measure, so I'm going to get rid of that error. Now that I know what to look for, I can definitely measure this a little bit better. Might even use something like a tape measure. Is a tape measure better than a ruler? Yeah, okay, so I might use a tape measure. Am I going to fix my speed calculations? Yeah, because I've got rid of the problem, this 2 metres. It's going to be far more accurate, isn't it? But what do I have to do, though? What am I going to have to measure? I'm going to have to measure this height, or this length of this ramp to use it in my thing. Path of the ball, I'm going to say half, because I know that I need to drop it a little bit clearer. And was the marble easier to drop than the other balls? Yeah. Because there's much more room on that ramp. I can think about this. I'm going to say half on this one too, because I may use just like something to hold the ball in place and then pull it out of the way. I don't know yet. I'm still thinking about that part of my redesign. And can I get rid of air resistance? So just simply by getting rid of this 2 meters, how many errors have I got rid of? 1, 2, 3, 4, 5, maybe 6, maybe 7 out of 12 that I've identified. Is my experiment going to be better?
Yeah.
So what should I find about these results? They should become
Closer.
closer. Okay, let's think about this. If I wanted to redesign it on Friday and I decided to get rid of the ramp. So I don't use the ramp. I'm just going to get something and I'm going to drop it. Have I got rid of my reaction time error? No. How could I do it better though?
Find a way to
Yourself?
press it.
Yes, good. I could do both. I could say, okay, and see if I can do them both at the same time. That's going to significantly reduce the reaction time of me saying to you, for instance, drop it now, and then press the stopwatch. Have I got rid of carpet?
Yeah.
Yep. Have I got rid of the bouncing?
Yeah.
Have I got rid of my ball problem?
Yeah.
Have I got rid of my side of my ramp?
Yeah.
Have I got rid of my measurement problem?
Yeah.
Am I going to have better speed calculations?
Yeah.
Do I need to worry about the path of the ball?
No.
Or do I?
You do.
Okay. What about the force used to release the ball? If I'm dropping it, that's probably going to be easier. Have I got rid of air resistance? No. So the only problem is if you get rid of the ramp, this actually becomes a problem. And if you're looking for that well above, I'm going to want you to talk about something extra. And I want you to talk about the Magnus Effect if you get rid of the ramp. Only for well above. Now, if you don't know what the Magnus Effect is, that's the point. I want you to go away and find out about it and why it would affect this experiment. So, look, that was a lot of information all at once, but that's okay because it's still recorded. Do you want me to put it on YouTube?
Yeah.
Okay, I'll whack it on my YouTube channel. You can have a look at that particular thing. Because this is packed full of errors and it was designed to be that way for you. So that you could actually be a scientist. Okay, I do want to point out a couple other things on this day, since we've got 5 minutes, it's not much point getting you to write something. So if we have a look at this, I want to talk about this kid's section. I'm going to read this for you. In addition, a person has an average reaction speed of 1.2 seconds, and when the amount of time is added for the stopwatch to start timing, the speed isn't accurately recorded. Now, the reason I picked this is because this kid, while he probably needed to look at the structure of it, he did write some fantastic sentences. Why is that a good one about error? What has he done in it? He specifically named up what he thinks reaction time is, which means he's probably had to go away and do what?
Research.
He's probably had to find it, like just basically by pressing Google and going, what's the average reaction time? And you can actually talk to Google now. Worked that out the other day. Who would have believed it? We have heaps of chats at my house. But
That's kind of sad.
he's always telling me information. He's one of those know-it-alls that Google got. But you can say, what's the average human reaction time? If the guy's actually done it and he's put it in. Is that impressive? Yeah, how long did it take you to do it? 3 or 5 minutes. 30 seconds. Yeah, 1 minute, 30 seconds, 2 seconds, just asking Google. And when the amount of time is added for the stopwatch to start timing, the speed isn't accurately recorded. So has this kid identified the error?
Yep.
And then he's named it up, and he specifically told me why it's an error. The amount of times I've had kids write this, timing is an error in my brain. They've tried. Have they named up the timing as an error?
Yeah.
They've said it's an error in their brain. They haven't said why it's an error. Okay? They haven't explained to me why timing is such a problem for this. This kid not only told me that timing was an error because of the reaction time, but he specifically related back to why it's affecting his experiment. He said that means that my times are all wrong, which means that my EK calculations are also all wrong. Okay, do you see what I mean about specifics?
Yep.
Now, that does take a while to write, so tomorrow is yours. Friday, you are going to repeat this experiment. Should really, how long did it take us to do the original one? 20 minutes. So you're going to repeat your experiment, however you designed it, around 20 minutes. And then what do you think we're going to do with the rest of Friday's lesson? This is yours. The rest of Friday's lesson is yours to write the scratch. So I have given you, wait, sit, don't move, Russia. I am going to give you 150 minutes to write this track. How many hours is that?
That's 1 hour and
Almost 2 hours.
40 minutes.
It's 2.5 hours, okay? So that is 2.5 hours that you have in class to write this practical for. If you don't use it, then that 2.5 hours transfers to your own time, and I would like to use that.